the method is more important one. Alright, so this question is just a basic Brayton cycle, as you can see from the diagram that I draw. So I've also noted down all the information that are given for this question here. So this gas turbine has an overall pressure ratio of 5. Maximum temperature of the cycle is 550. So this maximum will be at state 3. So that's why I know it as T3. So the question gives you an additional efficiency here. So the mechanical efficiency of the drive is 97%. So we can take this efficiency as the overall efficiency the work out of this system, the overall one. Then the ambient temperature is 20 degrees Celsius, and since we know that Brayton cycle takes air from the ambient itself, so T1 is 20 degrees Celsius, and mass flow rate of the air is 15 kilograms per second. And you are given isentropic efficiency of both compressor and turbine. Right. So first, you need to calculate the power output. So again, if you have power output, then net power output, I mean if the question states power output, we are always talking about the net power output. Okay? Unless we specifically say that it is the power from the turbine itself. Otherwise, we are always talking about the net power output. So in short, you need to find almost everything as usual. So let's start with the constant specific heat method. So assumptions, you should always include standard air assumption. And these two should always be there. Then for this question, we are using constant specific heat. Okay. So we look at process 1 to 2. So for constant specific heat method, actually for both methods, the methods are quite fixed. Okay. So since it's constant specific heat method, you can always use this method. So whereby here the question says that for compression process, you use K equals to 1.4, Cp equals to 1.005. So here we only need a K. So based on this, you should be able to get T2. Sorry, this one should be S. So this method always gives you the isentropic value. Then we can actually, so for now, you can actually choose to calculate for 2A or 2 based on the isentropic efficiency question. Or actually, you can just leave it here first. You can actually demonstrate to the process 3 to 4. So here also same thing. T3, T4S equals to T3, T4. From here, you can get T4S. So you should get this around roughly these two values. So A asks for power output. So this power output should be the mechanical efficiency multiplied by overall work net. Okay, because that is the efficiency of the whole price. So which means here it should be 0.97 multiplied by mass flow rate of the small work net, which is work out minus work in. So since we know that isentropic efficiency of the compressor is simply T2s minus T1 over T2 minus T1. As for the turbine is T3 minus T4 over T3 minus T4s. So technically speaking, you can actually just calculate work out and work in this way. So work in is just Cp T2s minus T1 over Nc, and work out is Cp T3 minus T4s. So actually you don't really need to calculate the T4a, T2 and T4 in this case. But obviously you are actually supposed to calculate T2 also, because after this the question did ask for thermal efficiency, which means you still need to calculate Q heat. So if you want to again, you can actually calculate T2 as well as T4, then just do it one step by step. It's the same thing. So this should give you the 660 kilowatt answer. Just be careful that these two Cp are not the same value, because the question says so. The 2K also are not the same value. Okay, this K and this K. So I will just quickly go through B and C. So B, you need thermal efficiency, work net over Q in. So from here, you can just use work net and Q in H3 minus Cp T3 minus T3. And then C is backward ratio. So this is just work in over work out. So once you have solved A, then B and C shouldn't be any issue, because it's just simply application of the equation itself of themselves.
Ui. Lấy súng để phải cho kiểu phải hồi đó
will have to be as usual lah. So you need to convert T1 once again into Kelvin first. So in this case 290 Kelvin. So you need to find H1 as well as PR1 from the table. But of course here this will be a bit more troublesome because you need to interpolate this value. And after that, what A is on PR1, PR2 equals to P2 over P1, you get PR2. Then from PR2 you get H2 S. So just similar to the previous question, all the methods that you learned on how to find the H, the T, they are all based on the isentropic version. They are never the actual one. Unless you are given the actual situation condition, then you just get they will have different pairs. So otherwise, they're almost the isentropic one. So meaning you still need to calculate to this equation to find the actual H2A, which is H2S minus H1 over H2 minus H1. Then process 3 to 4 also same thing. So you need to repeat T3. So for 3 and 4, Kelvin. So similar this one you still need to interpolate. So you will get H3 PR3, then PR3 over PR4 equals to P3 over P4. From here you need to find PR4 and then H4S. After that, yeah, same thing. Thermal efficiency of the turbine H3 minus H4 and then H3 minus H4S. So the difference is just the equation. The first one you use fully equation, second one use tables.